Any no comments? Okay, fine. That's great. Give me half a minute. Did you have time to go through this? What I sent yesterday? Are you there in the class? I've just logged in and left. I
Yes,
asked
sir.
you a question. There can be two answers. There cannot be any silence. Doesn't matter. Yeah. The number systems, many of you have studied in your class 11, 12. Binary number system. We all familiar with digital number system like digits 0 to 9. They constitute a digital number system, and from a very childhood we are familiar with this digital number system. Now that digital number system has base or radix. It is called a technical term. It's the base of the radix is 10. Okay, so when you have decimal number system, you have the digits as 0 to 9, and the numbers vary from 0, starting from 0, any number. Okay, and how it is calculated, for example, this number 332, the rightmost bit is called the least significant bit, and the leftmost bit is called the most significant bit. Now in the number system we will study four different types of number systems. One which we are discussing is the decimal number system. That means base is 10. uh, the other one which is very useful and very essential in digital logic circuits is binary number system, so which has a base of 2. Now now base of 2 means how many different types of digits, or it is called binary digits, are possible if the base is 2.
0 and 1.
0 and 1, yes. So there are many number systems, but four are very important. As I said, decimal number system, binary number system. The third one is a hexadecimal number system. That means you constitute the numbers as hex values. That means hexadecimal values. Okay, so the base is 16. Okay, so the fourth number system, which we will not study, but it is existing, is octal number system. Octal stands for obviously 8. Okay, but we'll skip this because the number of days available for classes is very small, and only this week, and after that we will not have classes, and we have to cover the number system, digital logics quite a lot. So let us skip the octal number system. Doesn't make any difference. This 332 number in decimals, or can be can be said like this, can be written like this. The rightmost digit is called the least significant digit because it has a weightage of 0. Okay, 10 to the power of 0. So how do you get the figure 332? The rightmost digit is 2. Rightmost digit is 2, so you write 2 in 10 to the power of 0, because the weightage of the position of this 2 is 0, 0th position, not 1. It does not start from 1, it starts from 0. Similarly, the middle 3 you write as 3 into 10 to the power of 1, because 1 is the position value or the weight, and the leftmost 3 is called the most significant digit. So you write 3 into the 10 to the power of 2. 2 is a position number starting from the right. So the position number starts from the right, 0, and then it goes towards the left, then 1, and then 2, and like this. Okay. Similarly for other number systems. So now,
স্যার,
yes.
স্যার বলছি কয়েকজন ঢুকতে চাইছে, অ্যালাউ করে দিন।
So binary number system similar to the decimal number system, but only the number of binary digits. You have heard the word bits. So binary digits is bits. Binary BI and digits T. The binary digit. So BI and then T from the digit. So it becomes bit. So if you have heard the word this much megabyte or this much gigabyte of memory, that is not bit. That bit, 8 such bits makes byte. Okay, bit makes byte. So both bit and byte starts with small. Both bit and byte starts with B, the alphabet B. So the bit is represented as lowercase b, and the byte is represented as uppercase B or capital letter B. Okay, so that is the binary bit or byte. Now the representation is like digital. The rightmost bit is the least significant bit, and the leftmost bit is the most significant bit. So you start from this. This is not a dot. There is a mistake here. It was mentioned as a comma in the original, but actually it is 1101. It is no such comma or dots are written in between binary digits. Okay, bits. So now, if 1101 has to be represented, so rightmost one multiplied by the position or weightage is 0. Then the 0 on the left of this 0. You write as 0 into 2 to the power of 1. Why 2 to the power of 1? Because the position value is 1. Then the 1 to the left of this is 1 into 2 to the power of 2, because the position value is 2. Like this you write, ultimately you arrive at 2 into 1 into 2 to the power of 3, that means 8, plus 1 into 2 to the power of 2, that means 4, and 1 into the power of 0, that means 1. This 0 into whatever is 0, obviously. So the the binary bit representation 1101 actually in decimal number system is 13. Okay. So now hexadecimal number system basically means there are in decimals you have 0 to 9. In binary you have 0 to 1. That means two bits, 0 or 1. But in hexadecimal stand from hexadecimal means 16. So the binary hexadecimal digits starts from 0 and up to 15. There are 16 such bits or binary hexadecimal digits. Okay, so from 0 to 15, total 16. That's why it's called hexadecimal. Now how do you represent these 16 numbers? You start from 0 up to 9 like in decimal, but after 9 how do you represent 10? 10 to 15 has also to be represented. They are represented as the alphabet 0 to A to F. Okay, they are represented as the alphabets A to F. So basically you have 0 to 9, then A, B, C, D, E, F. So for example, this number 1A5C, this is a hexadecimal number. This alphabets and as well as numericals mix is called a hexadecimal number. Like for example, the rightmost bit is hexadecimal bit is C. So C into position of that is 16. Here the base or the radix is 16. Not 2 for as 2 it was for binary, 10 for decimal, now it is 16. Okay, because it is a hexadecimal number. So the rightmost bit is the most least significant bit. It has the least. Why it is called least significant bit? Because it has the least weightage, 0. Any bit to the left of this C has more weightage, and the leftmost bit in this 4 bit number is actually the highest weightage. So the rightmost is called the least significant bit, and the leftmost is called the most significant bit. Okay, so it is like this. So C into 16 to the power of 0, then 5 into 16 to the power of 1, because the weightage is 1, then A into obviously 16 to the power of 2, and then 1 into 16 to the power of 3. Okay. So like this, you find out the weightage and the number, and you add them up. You get the equivalent of 1A5C of hexadecimal as 6748 of decimal. Okay, clear?
Yes, sir.
Yes, sir.
Many of you must have been aware of this. Now we have to convert this number system from one to the other. Do you know this conversion?
Yes, sir.
Yes,
So many
sir.
of you know. Those who are
Yes,
not
sir.
knowing, I will just repeat. You divide the this within bracket, and then at the base you write 10. That means it is a decimal number. So you have to represent it as a binary number. So you go on dividing by 2. You get whatever, suppose 66 you divided by 2, you get 33. Remainder you write on the right. Now next, the 33 has to be divided by 2. You get 16 and one remainder. So you write the remainder on the right. Now after we finish, that means there are no more thing to be divided. There must be a 2 here. So you get 1. Then the number representation starts from the bottom and goes to the top, not from the opposite. Some people make mistakes. They write 0 1 0 0 0 0 1. It is wrong. Actually it should be 1. Sorry, this 1, this one arrow I am pointing, this one, then 0. It is represented by this arrow. So you start at the bottom, go to the top. So this is a way to convert decimal to binary. Okay. So these are all without the decimal point. So 105.75, you do similarly. First separate the decimal part and the fractional part. So decimal, the integer part is 105. So you just do the representation as I have already told you. Now 0.75, you this after the decimal point, what do? You 0.75 you multiply by 2. So you get 1.5. So 1.5, you keep the 1, and the remainder part you again multiply by 2. So if you get the remainder part as 1, and then you get 0. So here the representation is from top to bottom. That you must be clear. After the decimal part, when you convert, you start from the top and go bottom. Not at the here it is just the reverse. It is from bottom to top. So it is now 1101001, and then after the decimal point, you start from the top. You get a 1 here and the 1 here. So it is 0.11. Okay, is it clear?
Sir, can you
Yes, sir.
explain the decimal part? I got
Which one?
disconnected this time.
Which one you want?
Decimal part 0.75.
Okay, so here this number is 105.75. Okay, 105, how to convert from decimal to binary, you are already knowing. I am not repeating this. You are going on dividing 105 by 2, and then you get 52, keep a remainder 1, then divide 52 by 2, you get 26, remainder 0. Like this you go on till you have that there is no further division is possible by 2. So then you go from bottom to top. So the 105 can be represented as 1 1 0 1 0 0 1. That means you go from bottom to top. But what about the decimal part? That is the fractional part. So 0.75. So instead of dividing by 2 or something, you multiply by 2. This is important. After the decimal part, you multiply by 2. So 0.75 into 2, you get 1.5. So keep the 1, like we are keeping this 1 or 0. So keep the 1 and take out the 0.5 part. So 0.5 part you get, and then next step you multiply by 2. So you get 1. Okay. So now how do you represent 0.75? You start from the top, not from the bottom. Okay. You get 1 and then 1, not from the bottom. Here it is same, but you should start from the top and go to the bottom. So 0.75 representation of decimal in binary becomes 0.11. So you now club them together, you get this for 105 you get this binary bits. It is called a stream of bits. Okay, so you get this stream of bits to the left of the decimal point, and to the right of the decimal point is like this. Now it is clear, Anna?
Yes, sir.
Now example of binary to decimal conversion. Suppose you have a string string of numbers. decimal, sorry, this is the binary numbers or binary digit. So it is called bit. From now on, I'll call this as bits. So this is a string of bits. So you sometimes write the base or the radix after the bracket with it in a uh, suffix form. Okay, suffix form. So here you basically this I have mentioned. It should be easier for you to write in reverse order. Okay, why reverse order? Because you don't know where it will end. So you actually best is to start from the right. So you write this rightmost bit is the least significant bit. Excuse me. Sorry. This rightmost bit is the least significant bit. This you multiply by 2 to the power of 0 because that is a weightage in this position, rightmost position. After that, it is 1. So this 1 into 2 to the power of 1. After that is 0. So you write 0 into 2 to the power of 2. Then again 0. You write 0 into the power of 3. Like this you continue. So this is the 0th position on the rightmost. Then one position. That means 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6, 2 to the power of 7. So the leftmost bit is the most significant bit because it has the highest weight. And that is written as 1 into 2 to the power of 7. Clear? So you add them up, whatever you get, and you get the decimal equivalent. So that is a binary to decimal conversion. This is same exactly, but here you have a decimal. This is a there is a decimal point here. There is a binary string of bits, but a decimal point. So this 1.101. How do you do after? See this this least significant bit 1. You multiply by 2 to the power of 0. Now what happens to the one to the bit on the right? So you multiply this bit as 2 to the power of -1. Okay, after the decimal place, it goes on -1, -2, -3 like this. Is it clear?
Yes, sir.
So this is 1 into 2 to the power of -1. The 0 is 2 to the power of -2. This last one is 2 to the power of -3. If it was another bit, if there would have been another bit, it would have been 2 to the power of -4. Like this, it goes on. Now you get all these things. So 1 into 2 to the power of -1, 2 to the power of -1 is basically half. So you write 0.5. This is 0, and this is 1 into 1 by 8. So it is 0.125. So add them up, you get some number. Decimal to octal, I'm not doing. I'm not doing anything about octal number now. Octal is out. Is not so useful for your purpose. Now decimal to hexadecimal conversion. Suppose there's a decimal number 527. Okay, what like we know 527. So when we converted decimal to binary, we started dividing with 2, dividing by 2. When you convert a decimal to hexadecimal, you divide by 16. So divide 527 by 16, you get 32 as the quotient and the 15 as a remainder. Keep the remainder like that on the right. Then divide 32 by 16, you get quotient 2 and remainder 0. So again, like in binary conversion, you start from the bottom and go upwards. So the equivalent of 527 is 20 and 15. Okay, so 20, 15, but you cannot write 15 in hexadecimal because in hexadecimal to represent 15 you have to write F. Okay, so 20F. I said in hexadecimal the bit starts from 0 and ends in 15. There are 16 such numbers, so 15 is actually the F. Hexadecimal representation is from 0 to 9, then A, B, C, D, E, F, total 16. So 15 is represented as F. Similarly, if you have a decimal point, then before decimal you are knowing already. After decimal, this 0.675, you multiply by 16. So you get 10.8. Keep the 10, take 8.8. So 0.8, you again multiply by 16, you get 12.8. Keep the 12, you get 0.8. So this 0.8 is going on repeating. There is no end here. So they have stopped after some time. So actually, this is, you again, when it is before the decimal place, you go from bottom to up. When it is after the decimal place, you go from top to bottom. So here you have 10, 12, 12, 12. So after the decimal place, that number is, hexadecimal number is 10, 12, 12, 12. Now what is 10 is A. You'll get habituated with this later on. 10 means A, 12 means C. So you get after the decimal place A, C, C, C. And before the decimal place 1, 2. Okay. So basically the number 18.675 can be represented as 12.ACCC in hexadecimal. Clear? Just like binary, but only thing, the you use 16, not 2 for the division or the multiplication. Division before the decimal place is 18 and multiplication by 16 after the decimal place. Is it clear? The hexadecimal to decimal conversion. Suppose you have a hexadecimal number A3F. How do you know it's a hexadecimal number? First of all, from the characters you can understand it can only be hexadecimal. A, F, all these are alphabets. So A3F is a hexadecimal number. You convert into decimal. So you start A3F. So you start from the rightmost. F is 15 actually, and the position weight of this is anything, the 16 to the power of 0. Now the next hexadecimal number is 3, so you multiply 3 into the power of 16. The next number is A. A is actually 10, so you multiply 10 into 16 to the power of 2. The position weight is 2. So you add them up, you get this number. Is it clear?
Yes, sir.
Now again, you can convert hexadecimal to binary. You can convert one from the other. Only leave out octal. Don't study octal. Hexadecimal to binary. Suppose you have a number 34F. This is a hexadecimal number, obviously. So this hexadecimal number you convert to binary. Each hexadecimal number you convert to binary and you get the total number. For example, the 3 is actually in binary 011. If you find what is the binary equivalent of 3, it is 011. Okay, sorry, 0011. Hexadecimal has to be 4 binary bits. 3, then 4. 4, it will be 0100. And F will be 1111. Okay, so it is 3. So instead of 3, you write 0. This part 0. This part 0011 instead of 3. Then the number is 4. 4 is 0100. And the last F, instead of last F, you write 1111. Okay, clear?
Yes, sir.
Yes, sir.
Now after the decimal, if you have a hexadecimal number with a decimal point, so this is a hexadecimal number. You can understand A, F, B, C, B, E, D. So first of all, since you're not familiar with hexadecimal, you write all the hexadecimal bits as binary. Okay, so once you are habituated with this, you can write without doing anything. But as of now, we have to write them down. So A is 1010. Okay, it's actually 0 to 9, then A to F. So 0 is 0000, 1 is 0001. Okay, like this. So you have to get habituated with this, how to write this. A is 1010, F is 1111, B is 1011. How you get this? Actually, you have to convert. No, I have told you how to convert this number. You make a chart, like in our childhood, you used to remember the tables, remember? 1 into 1, sorry, say table of 6. 6 into 1, 6, 6 to the 12, 6 3 is 18. We used to remember by heart. So you please make a chart of all the binary hexadecimal numbers, and you will get the binary equivalent number. Okay. So 0 will be 00000, 1 will be 0001. Like this, you get habituated with that. So here you have is when you represent this hexadecimal number as binary, it's a big string of bits. Okay. So how do you get? So first A you write 1010. So first, the most significant hexadecimal bit is A. So we replace A by this equivalent binary number. So it is this 1010, first 1010. Then it is F. F is 1111. So you represent the next 4 bits as 1111, like this. Clear? Concept is clear. You have to go through them. Have some practice. At the end of this digital logic class, I'll send you the collection of all question papers as an assignment. Don't have to submit any assignment. It is just for your knowledge, so that you can see what types of question had come in earlier years. Binary to hexadecimal conversion. Suppose you have a binary string. It has to be multiples of 4. So this is 4-bit, and this is again 4-bit. Total 8. So it's very easy. So 1001 you convert to hexadecimal, it is actually 9, and this 1100 you convert to binary, it is 12. But what is 12 in hexadecimal? It is C. So this becomes C9. Clear?
Yes,
Here
sir.
one thing I have to tell you. If you have such a string of numbers which are binary bits, you have to convert to hexadecimal. So here one thing you have to remember is the grouping. So take decimal point as the starting point. Okay. Then you go left and then you go right. So from the decimal point you collect or group 4 bits. So it is 101011. So you write 1011 separately. So and at the bottom of 1011 you write that hexadecimal equivalent of that string. So 1011 is B. Then you write next 4 bits. What is that? 1101. So this is 1101. So at the bottom write D. 1101 is D. And what is left? What is left?
0010.
No. What is left after the left?
10.
10. So what you have to? I said you have to group in 4. So if 10 is not 4 bits. So one instead of 10 you write 0010. Okay, because we learned from our childhood, if you add zeros to the left, it doesn't make any difference. So we add as many number of zeros so that it makes 4. So 10 was there. So I took 10 from there, and then I add another 2 zeros to the left. Clear?
Yes, sir.
So this 0010 becomes 2. Clear?
Yes, sir.
Now what happens to the right of the decimal place? I told you start always from the right, from the decimal place. You go left, collect 4, then again collect another 4, and if you cannot have 4, you make it 4 by adding zeros to the left. Now after the decimal place, you collect 4 again, not from the right, but from where the decimal point ends. So it is actually 0, 1. So this 0, can you see this 0, 1, 1, 1? So I collected 0, 1, 1, 1. Okay. So I collected 0, 1, 1, 1. Clear? After the decimal place,
Yes.
I collected 0, 1, 1, 1. So after I collected 0, 1, 1, 1, what is left?
1.
After I collected 0, 1, 1, 1, what is left?
1.
Single 1 is left. So I bring it down and add zeros to the right of it. After the decimal place, if I add 0, doesn't make any difference. Before the decimal place, if I add zeros to the left, doesn't make any difference. So I have to make groups of 4. So 1, I'll make groups of 4 as 1000. So 1000 equivalent of this is 8. Clear? So the total binary string gets equal to 2DB7, 2DB7, sorry, 2DB and then the decimal place and then 78. 2DB a decimal place and then 78. Is it clear?
Yes, sir.
Yes.
Now, octal forget. Don't have to study octal. Now we'll start with something which you have not studied earlier. So this is called complements. What are complements? Complements are used in digital computers because we are studying digital logic. From now today, we are studying digital logic. We have completed our analog part. So in digital computers, complements are very useful. So from now on, we will be studying mostly binary numbers, binary bits. So complements are used in digital computers, simplify the subtraction operation or for logical manipulation. Okay. Now there are two types of complements for each base R system. Base R means I told you base can, if it is base is 2, then it is binary. If base is 8, then it is octal. If base is 10, then it is decimal. If base is 16, then it is hexadecimal. So for either of these number systems, you can have two types of complements. One is R's complement. R's, what is R? R actually stands for the base of the radix. R stands for radix complements or R's complement. So R can be either 2 for binary, it can be 8 for octal. This R can be 10 for decimal and R can be 16 for hexadecimal. There are 4 number systems which you are studying. So octal you don't you know that it is there, but don't have to study. R's complement actually of any number can be found out from this formula. Okay, what is this formula? I'll tell you, don't worry. So R's complement is a generalized term. Okay, R's complement, if R is radix, can be what are the different types of radix?
Four.
4. So what is the first one? For binary, what is R?
2.
2. Okay. So for binary system, we can have 2's complement. I substitute R by 2. Okay, so we can have 2's complement. For decimal number system, we can have what? 10's complement.
10.
Okay, like this. So this is one type of representation, R's complement. This is called radix complement. Radix stands for R actually. So another is diminished radix complement. What is diminished radix complement? Now earlier we had R's complement. Now we will have R minus 1's complement. Okay, R minus 1's complement. So for binary number system, what does it mean?
Two's complement and one's complement.
Very good. For this we have 2's complement and for this we have 1's complement. For decimal number system, what are the two types of complements?
10 and
10
9.
and 9.
10 and 9. Very good, excellent. So for if you have the R's complement as like this, then the number is this. What is this? I'm coming for R's for say any R's complement, 2's complement or 10's complement, whatever. For n must be 0. Okay, but if you have R minus 1's complement, for example 1's complement or 9's complement, then it is given as, the earlier one was R to the power of m minus 1. This is m, and this is R to the power of m minus 1 minus 1, one less than the earlier one. Okay, now we'll go to examples. Everything will be clear. For example, decimal number system will have 10's complement and 9's complement. This we have, I've already told you. Similarly, binary number system will have 2's complement and 1's complement. Okay, now how to find the 10's complement? So here, okay, what is the formula? R to the power of m minus n. Now I'll come what is the different numbers. R is radix of the base. For binary it is 2, for decimal it is 10, like this. What is m? M is the m number of digits in the number. The number is capital N. the number is capital N, and small m is the number of digits in that number. For example, what is m in this case?
4.
4.
4. Very good. And what is n in this case?
2657.
Very good. So tens complement of 2657 I have to put in this formula. Don't look down. Tell me 2657. What is it? What can I write for this? What is the tens complement of 2657?
10k power 4 minus 2657.
Very good. Excellent. 10 to the power of 4 minus 2657. So 10 to the power of 4 is this. To subtract 2657, you get the tens complement of 2657 as 7343. Clear? Now, what is the nines complement of this number? 2657. I have to put it in this formula. Actually, the earlier formula minus 1. So let us use this formula for 2657. What is this? What should it be then?
10.
বলো একবার তো বলো।
10.
10 to the power of 4
4.
Number 4 minus 1
minus
minus
1 minus
2657.
very good. So 10 to the power of 4 minus 1 is 10. This is 10 to the power of 4 minus 1. You get 9999. This is 10 to the power of 4 minus 1. And from that you subtract this number 2657. So what do you get? 7342. What did you get earlier? 7343. So 9's complement is 1 less than the 10's complement. Clear?
Yes, sir.
So I told you the r's complement is 1 more than the r minus 1's complement. So r minus, so if you add 1 to the r minus 1's complement, you will get the r's complement. Now coming to binary number system. How to get the 2's complement of any binary string. So the binary string given here is 101101. So apply formula r to the power of m minus n. What do you get?
Two to the power 6 minus the number 101101.
Excellent. Excellent, excellent. So this is 2 to the power of 6. 2 to the power of 6 is this. 2
Yes,
to the power of
sir.
6, how do you write? You write 6 zeros and then a 1. Okay. From that you subtract this number itself. Number is 101101. So from this number you subtract this number. Do you know how to subtract binary numbers? Do you know how to subtract binary numbers?
No, sir. No, sir.
So concept is similar to any decimal number. For example, we know this. I never how to do this subtraction. How to do this subtraction from, suppose this is a decimal number. I want to subtract 2657 from 10,000. So upper number 0 is more than the lower number. 0 is less than 7. So you cannot subtract 7 from 0. So what you have to do, you have to take a carry. Is it not?
Yes, sir.
So first of all, you take a carry from this, the leftmost part. So you get 1 0 now. So 1 0 minus 7 is 3. So when you took a carry from this number, what you would have got? You carried 1 from this number. From 1000 you carried 1. So what is left? This is class 3 mathematics.
9,999.
Yeah, not 9,909. Who said? From 1000, if you take subtract 1, you get 9000.
999.
सर
Very good.
9999 ही बोला था.
No. You're taking, just try to understand. See, first digit is 0. So I cannot subtract 7 from 0. So I take a carry from this 1000. From the left 1000, I take one carry. And then I get 10, and then I get 10 minus 7 is equal to 3. Clear? But when I take a carry from this 1000, I am left with 999. Class 4
Okay,
mathematics. So I get 999. So once I get 999, I can subtract 2657 because all of them are less than 999. From 9 I subtract 5, I get 4. From 9 I subtract 6, I get 3. From 9 I subtract 2, I get 7. Class 3 mathematics, arithmetic. That time it is called not mathematics but arithmetic. Clear? So this is subtraction of decimal number. Why I stressed on this? Because the same concept is followed here. So when you subtract this number, binary number, and this is the first bit is 1, and here the first bit is 0. So we cannot subtract. So you have to take a 1 from this left positions. You have to take a 1 from this left position. So you get 1, 0. 1, 0. 1, 0 is actually 2. 1, 0. In binary is actually 2. So 2 minus 1 is 1. Clear? And what about if when you take a carry from this, you get 1, 3, 4, 5. You get 5 ones. Yes or no? When you carried 1 from here, you carried 1 from here, you get 1 less than this. So 1 less than this is 999. Similarly, when you carry 1 from this number, you get 5 ones. Yes or no?
Yes, sir.
Yes, sir.
So you get 5 ones. So first rightmost bit, you get 1, 0 minus 1 is 1. And from this ones, you subtract these numbers. From 1, if you subtract 0, you get 1. From 1, you subtract 1, you get 0. From 1, you subtract 1, you get 0. Oh, 0, right. From if you subtract 0 from 1, you get 1. If you subtract 1 from 1, you get 0. Clear? Same concepts, but now you must get familiar with binary bits. Clear?
Yes,
Now
sir.
the same string 101101. Okay, I write here 1011. Now here on the example 34, it was 2's complement. Now the example 35 is 1's complement. So 1's complement is what? R to the power of m minus 1 minus n.
Yes, sir.
So r to the power of 2 to the power of 6 minus 1 is this number. From this, that you subtract the number itself. Okay. So you get bit by bit subtraction you do. From 1, you subtract from 1, you get 0. 0 you subtract from 1, you get 1. 1 you subtract from 1, you get 0. 1 you subtract from 1, you again get 0. 0 you subtract from 1 is 1, and 1 minus 1 is 0. Okay. So this is 1's complement. Clear? Don't have to bother your head. Huh? Bolo? Now this is the mathematical formula. You feel this is very complicated. Okay. Now there is a very easy way to find out the 2's complement or 1's complement of any binary number without going through all this formula. This is the formula. That means the basis on which this is done. For example, to get 1's complement of this number, what you do? You just invert all the bits. So instead of 1, you write 0. Instead of 0, you write 1. So what do you get?
010010.
So 0, 1, 0, 0, 1, 0. So this is a complicated formula. You have to do 2 to the power of 6 minus 1 minus n. Now do subtraction, do all these things. By the time you end at the result, you get a wrong result. So easiest way, the trick is to invert all the binary bits. You'll get a ones complement of that. Clear?
Yes, sir.
Yes, sir.
Okay. So now to how to get 2's complement of this number, there is again a trick. So start from the right. You encounter a 1. Suppose there was a 0. Suppose I'll take you the simple example. Suppose this is a binary string. So you start from the right. You start from the right. What do you get?
0.
So you keep the 0. Okay. Then what do you get?
1.
1. Okay. You keep the 1. That means you have now starting from the right. Very important. Starting from the right, you have encountered a 1. First you get a 0. That is not a 1. So you write 0. Then you encountered a 1. Write the 1. Then stop. Then stop. So what do you get? From the right, you get wrote 0. Then wrote 1. You stop because you have encountered a 1. So what do you do with the remaining 2 bits? You invert them. So what do you when you invert them? What do you get?
So 01001.
I told you
One,
you have
one.
you encountered the 0. You write 0. You as your answer. Okay. I want the 2's complement of this number. Okay. So first step, I start from the right. I get a 0. I write down the 0. That it is part of the answer. I get a 1. I write down the 1 because that is part of the answer. And then I stop. Why I stop? I have to invert the remaining bits. If there are 10, 20 bits, I have to invert all of them. So if I invert, once I encounter the 1 from the right, I stop. Because I have written as the answer 0 and then 1. First in the answer part, I have written 0 and then I have written 1 because I have encountered a 1. Then stop. Don't write anything else. Then what do you write as the answer? Inversion of the remaining bits. So what is the inversion of the remaining bits?
01.
It
01.
becomes 0, 1. So total answer is what now?
1110.
Mm-hmm.
0,
1.
1, 1, 0.
0110.
Very good. 0, 1, 1, 0. So I start from the right. That will be part of the answer if it is 0. If I get another 1, it will be part of the answer, that is 1. But then I don't write anything else. I just invert and then write. So I invert, I get it 0, 1, and then I've already written as part of the answer 1, 0. So it becomes 0, 1, 1, 0. Am I clear?
Yes, sir.
Fast. Can you tell me fast? What is the 2's complement of this number?
So 1100.
Very good. Excellent. Who said this?
Sir Rajat.
Huh?
Sir Rajat.
Okay, excellent. What is the 2's complement of this number?
So 0010.
0, 0, 1, 0. So you have got it. Anybody? Apart from Rajat. 2's complement of this number?
0100.
0000.
No. Who said 0, 0, 0, 0?
2, 1, 0, 0.
Huh? What is the 2's complement of this number?
Sir, 0100.
Very good. What is the 1's complement of this number?
0011.
Very good. What is the 1's complement of this number? Sorry. What is the 1's complement of this number?
01110.
Very good. What is the 2's complement of this number?
01111.
Very good. I'm taking any random number. What is the 1's complement of this number?
1001010.
Very good. What is the 2's complement of this number?
One
One
zero
zero one
one
zero one.
1
এক এক করে ওয়ান বাই ওয়ান একজন বলো যে কেউ
1001011.
Very good, excellent. Now you have got it. So this complicated formula now you can forget. But suppose somebody once tells you to derive this, then you have to answer, okay? But the trick you have not understood. Now you have understood any binary string, you invert, you will get 1's complement and 2's complement. I told you the logic. Start from the right, you encountered it once, write the one, then stop. And remaining bits just invert. Okay, clear? So this is very good. Now you have understood. Now some important things: subtraction with complement. Now you know what is complement. Now we have to do subtraction, because in computers they never use subtraction. They can only add. How do they add? Suppose I want an answer to this number, answer to this question: what is a minus b? But the computer cannot do any subtraction. Big problem. So what happens? You have to add. You have to find the 2's complement of b and then add with a. You'll get the answer. What answer you'll get? A minus b. Clear? So a minus b is what? A plus 2's complement of b. What is highlighted is 2's complement of b, is it not?
Yes, sir.
So I'm not subtracting b from a. I'm adding. This is an addition operation. I'm adding what? 2's complement of b to a, and I will get the answer a minus b. This is the actual how it works. Now suppose I have two numbers, a and b. A is 1100 and b is 1010. Can anybody tell me what is the decimal of this number a?
12.
Very good. Ananya baad diye, apart from Ananya, anybody tell me what is the number of, what is the
10
decimal? Huh?
10
10. Very good. So what I'm supposed to do? I have to subtract 1010 from 1100. That means I have to subtract 10 from 12. Is it not?
Yes, sir.
So I have to subtract 10 from 12. That means 12 minus 10. What is 12 minus 10?
2.
2. So let us find out whether we'll answer should get 2. No. So what do? I have to do 12 minus 10. So that means 1100. A is 1100 minus 1010. That is 2. Okay. That is B. A is 1100 and B is 1010. So A I write as it is. For B I write 2's complement. What is 2's complement of this?
0110.
0110. So very good. So instead of B, I write 2's complement of B, and then I add them up. So 0 plus 0 makes it. I write 0. 0 plus 1, I write 1. 1 plus 1 is how much? 1 plus 1 in decimal is 1 plus 1 is 2. So 2 is actually 1. 1 plus 1 is 2. 2 is means decimal 2. So decimal 2 is represented as 10 in binary. So 10, I write the 0 and carry the 1. Suppose 9 plus 7. 9 plus 7 is 16. I write 6 and carry the 1. Is it not? 9 plus
Yes,
7 is
sir.
16. I write 6 and then carry the 1. So 1 plus 1 is actually 10. So I write the 0, carry the 1. So carry the 1 to the next step. So on the top is 1. So 1 plus 1 plus 0 makes it again 1 0. Clear?
Yes, sir.
So I have now got a see. Now this mathematically you can understand a minus b is a plus 2's complement of b. I have done. What I am doing here?
A plus B complement.
I have added 2's complement of b to a. So if I rearrange, I will get a minus b plus r to the power of n. So this r to the power of n now must be discarded to get a minus b. Till now, what I have done, a plus 2's complement of b. This what I have highlighted is a plus 2's complement of b. So a plus 2's complement of b is actually a minus b plus r to the power of n. But what I need is a minus b. So I discard the carry. So this carry, the leftmost bit is discarded. Discarded means you subtract. You get this 0 0 1 0. So 0 0 1 0 is actually 2. So my quest was to do 12 minus 10 subtraction. So 12 minus 10 subtraction, my expected result is 2, but which I am getting now.
Sir,
Is it clear?
sir, you said that computers can't perform subtraction. So how can sir this be subtracted like 1 0 0 0 0? How is it
They
being
don't
subtracted?
subtract. Yeah, raised this question? Absolutely very good question. I'm very happy with you.
Sir Rajat.
Yeah, absolutely correct. It will not do this subtraction. It will just discard the leftmost bit, which is equivalent to the subtraction.
Okay, sir.
For our purpose, we are discarding means discard carry. So discard carry means just remove this bit. That is equivalent to subtracting. No? It will not subtract. You are absolutely correct. We are trying to avoid subtraction, and then we are adding some subtraction step, which is not correct. It is just to show actually it will discard. That's why it is written explicitly. Discarding carry is equivalent to subtracting r to the power n from the result. You get me?
Yes, sir.
We are showing as subtracting r to the power of n, but that is equivalent to discarding the carry. I will just blindly discard the carry and I will get, that means this bit if I discard. So what I am left with 0 0 1 0. That is my answer. And that is tallying with what we should expect. Now 12 minus 10 we are doing. 12 minus 10 answer should be 2. So if I discard the carry, I will get this answer. Clear?
Yes.
So that is one thing issue. But suppose A is less than B. So if I have to do 10 minus 12. So now A is 10, B is 12. So I have to now do A minus B. So what do I get? I get a negative answer. Yes or no? I should expect a negative answer. Yes or no?
Yes, sir.
Yes, sir.
Okay, so what is A now? A is 1 0 1 0 and it has now changed. It is not same as earlier. B, it has interchanged. A is now 1 0 1 0 and B is 1 1 0 0. Now I have to do A minus B again. So what is A minus B? A plus B's complement. Yes or no? A plus 2's complement of B. Whether I do A minus B, then A is greater or B is greater, doesn't matter. We have to write A minus B as A plus 2's complement of B. Yes or no?
Yes, sir.
So what is, I write down A as it is 1 0 1 0. So and write 2's complement of B. What is 2's complement of B?
0 1 0 0.
So I write 0 1 0 0. And then I add them up.
Yes, sir.
Now if I add them up, this is easy addition. Can you relate this addition? What do I get?
1110.
1 1 1 0. Now in this case, no carry is generated.
Yes,
That is
sir.
that is an indication to the computer that the result is a negative number. If there no carry is generated, if you add two numbers, then it indicates that it is a negative number. So I have to take 2's complement of the result. That will be the answer. 2's complement of the result is how much?
0010.
0010. So 0010 is 2, and I have to take a negative of that. How to take negative? I'm coming, just coming. Next topic is that. Is it clear?
Yes, sir.
Uh, Now, till now, what we have done in this 4.1.1, we have subtracted two numbers using 2's complement. R's complement method. That means radix component complement. That means 2's complement. Yes or no? Topic 4.1 is subtraction with complements. It has two parts. 4.1.1. That means subtraction with complements using R's complement method. That means 2's complement in this case. Now we'll do the next 4.1.2 using R minus 1's complement. So in this case, it is 1's complement. For binary number, R is 2, so it is 1's complement. Earlier one, what we are discussing is 2's complement method. Okay? Clear?
Yes, sir.
Sir.
Now this step, let us do with questions may come in the examination. Subtract two numbers using 1's complement or 2's complement. So if it is 2's complement, do whatever has been taught till now. For what 1's complement, what we have to do now is find out this. So basically using 1's complement. So for A minus B, the A is 12 and B is 10. So A is greater than B in this case. So A minus B is A plus 1's complement. Now, not 2's complement. So A I write down as it is 1100. What is 1's complement of B?
0101.
Yes, very good. So it is 0101. Now add them up.
One
Add
zero
them.
zero zero one.
So I get 10001. In 2's complement method, we discarded the carry. In 1's complement method, we have to take the carry out and add with the remaining part. There, that is the regular rule. Why I'm telling the rule coming there. So you take out the end out carry, place it here, add with 0001. So what do you get? This number.
Yes, sir.
This is the rule. But why is this rule there? There must be some logic. Why you have to subtract? And sorry, why you have to add this end around carry? Because now we are using 1's complement. Now 1's complement is result is 1 less than the 2's complement. Clear or not? Earlier we have seen, even we have seen that 9's complement 7342 is 1 less than the 10's complement. Yes or no? We have seen this.
Yes, sir.
Similarly, 1's complement is 1 less than 2's complement. 9's complement is 9's complement is 1 less than 10's complement. Similarly, 1's complement is 10's 1 less than 2's complement. Clear or not?
Yes, sir.
So because of this, the sum produced is 1 less than the corresponding difference when an end array the sum which we have got is 1 less than the correct difference when an end carry occurs. Therefore, end carry will be added to the sum. Is it clear? Now we are dealing with 1's complement. So when we have got 1's complement, we have got something which is less by 1. So we have to add this end around carry. Okay. So just remember this rule. Logic is this. If you remember the rule, it's also fine. But now if we have to do b minus a, they have kept the number same. Now we have to write b minus a. So b minus a is second case. This is the first case with 1's complement. This is the second case of with the 1's complement. In this case, it is a. The a is greater than b. Here b is greater than a. So actually, what we do, we have to do b minus a. So b is 1010. We write b as 1010. Instead of a, we have to take 1's complement of a. What is 1's complement of a?
0011.
So we take 1's complement of a. We write 0011. Then we add them up. If you add them up, what do you get? This we get
1101.
1101. Now there is no end around carry, so we don't have to add. In 2's complement, there was an end around carry. We discarded the end around carry. In 1's complement, you added the end around carry. Now in 2's complement, what we have seen, we got this result. Now this result, we have to take 2's complement to get the answer, because it was using 2's complement. Now this answer we got, we have to do 1's complement to get the answer. What is 1's complement of this?
0010.
So 0010 is the answer with a negative sign. Okay, you have to do a little practice with this, so you'll get that clear. Now let us come to the sign. How do you say minus? How does the computer know minus? It cannot sense that minus sign. No, we can sense, but computer cannot sense. So there is a system. There are two systems. Okay, one is sign magnitude convention. One is called sign magnitude convention. Another is signed complement system or convention. Is it clear? Is it clear?
Yes, sir.
Yes, sir.
There are two ways to represent a sign magnitude. Okay. One second. So one is a signed magnitude convention, another is signed complement. You can say convention also. So signed is common in both. So you have to give a plus sign or a minus sign, either magnitude way or complement wise. How to do magnitude wise? So what is 24? 24 is actually this. Okay, 24 is 11000. That is 24 in binary. So sign magnitude, you have to add another bit to the left. That is called the sign bit. So 24, if you add a 0, it means plus 24. Computer understands this number as plus 24. To this 11000 for 24, if you add a 1 on the left, you get a minus 24. Okay. Is it clear? This is called the sign magnitude. So whether the leftmost binary bit is 0 means positive, 1 means negative. This is a sign bit. The computer understands that 24 can be represented as 11000. So when it finds an additional bit, it will understand that it is a sign bit. So if they find the number starting with 0, it means a positive number. If the number is starting with 1, it means a negative number. Clear?
Yes, sir.
So this is called the sign magnitude. The magnitude tells you whether it is this or this. What is a sign complement system? Here, sign complement. Okay, sign complement can again be of two types: 2's complement or 1's complement. That you are already aware. Yes or no?
Yes, sir.
So in this, what is 24 in binary? First tell me.
One one zero zero zero.
Yeah, very good. 11000. That is the 24. Okay. So if now we write with a 0 on the left, that means plus 24. 24, I'm writing did you get me? Are you getting me? I can write in sign magnitude 24 as 0 for the sign bit and 11000. Yes or no? Now the minus 24 representation, I am representing plus 24 in sign complement representation, same as in the sign magnitude convention. So plus representation, positive number representation in both convention, sign magnitude and sign convention are same. Is it clear? First try to understand. In sign magnitude, this is the plus 24. Yes or no?
Yes, sir.
So same for the other system. For representing plus 24, it is same. Okay. Now minus 24 in sign magnitude is leftmost bit is 1, other bits are same. Now now plus 24 representation in both convention is same. So how to represent minus 24 in the other convention? So minus 24, you take the ones complement of this. The ones complement of this is what?
100 111.
Yeah, 100 111. This is minus 24. In sign complement convention. Okay. And minus
Yes, sir.
24 in 2, what is the 2's complement of this?
1 0 1 0 0 0.
What? 2's
1
complement.
0 1 0 0 0.
Very good, very good. 101 000. Okay, this is 2's complement representation of minus 24 in sign complement system. Okay, just a second, I'm coming. Till now, everything is clear. Plus
Yes.
24 in both system is same. Minus 24 in sign magnitude system is what? I told you. Just a recapitulation.
1 the 11000.
11000 is the number 24. What is the sign bit? In sign magnitude convention. Sign magnitude convention. What is minus 24?
111
Huh?
111
Yes. The sign bit is 1 and then the number itself. That is minus 24 in sign bit. Minus 20 plus 24 in sign bit is 0 1 1 1 0 0 0. Plus 24 is in 2's complement representation is same. Okay, plus 24 is same in both cases. In sign magnitude, you represent minus 24 with a 1, starting with a 1 and then number. In ones complement representation, you take the ones complement of this to get the number, to get minus 24. In twos complement representation, you take the twos complement of this to get the number. Is it clear?
Yes, sir.
Yes, sir.
Okay. You can go through some of these examples. Some solve this. Don't have to go through this one. This page you can, the last page you can ignore. There are some questions. If you want, you can go through and the multiple choice questions. If you want, you can go through and make your concepts clear. If you have any doubt, we can discuss in the next class. Okay. So we'll take a short break because we'll have to now do Boolean algebra. Okay. We'll take a short break of 5 minutes. And regarding Wednesday's class, can we start at 9 o'clock? 9 to 11, not 12. I have some work at 11 o'clock. Or if it's not possible, then we'll start at 9:30. Sears.
Yes, sir.
So 9:30 or 9? Up to 11. Okay, 9:30. Bishwadeep is messaging 9:30. So we Wednesday we start at 9:30 up to 11 o'clock. And what about another class? I told you we need to have that class to complete whatever is required. Sears. Bishwadeep, message me. I told you 1 week in advance. সাগরিকা কি লগ ইন করে চলে গেছে নাকি? প্রিয়াঙ্কা, বিশ্বদীপ, fine. Bishwadeep, you, Priyanka and Sagarika, you decide what time you will have the third special class because we need to complete the syllabus. Okay, fine. So we have a break of 5 minutes and then we'll start the Boolean algebra. Can we start now?
Yes, sir.
Sir, Saturday 10.
Saturday 10 o'clock.
Hmm.
ঠিক আছে, এটা মেসেজ করে দাও না আমাকে।
আচ্ছা।
One minute. So basically now we will do Boolean algebra. So Boolean algebra, you are aware of this? Anything you know? You heard a little from,
Yes, sir. We did it in computer science
Yeah.
in class.
very good. So others also, you got a little introduction when Shamoli ma'am gave the introduction while taking the lab, remember? So basically we have different types of gates. The basic gates are of three types. One is a NOT gate. NOT gate symbol is like this. You have an input and the output is an inverted form of the input. Okay, so basically this inversion is represented by a bubble. In all these symbols, the negation or the complement form of something is represented by a bubble. So you get y as it is called the complement of a or the negation of a. So whatever you give a, you get the opposite or the complement of that. So if you give 0, you can have, now we are in the binary number system. We'll forget now about other number systems. Now for input 0, you get the output 1. That means the inversion of this. It is called NOT gate, okay, or it is called the actually complement form, and it is represented a with a bar on top. Okay, so a bar means y is basically a of bar, means whatever you have a, the complement of a is y. So if you have a as 0, if you give the input 0, output you will get 1. If you give the input 1, you will get output 0. Okay, this table is called the truth table, which relates the input and the output. Okay, is it clear?
Yes, sir.
Now in this you have only one input. In an inverter, you cannot have you cannot have 2 or 3 inputs. Other gates you can have more than one. You have to have more than one input. You can have 2, you can have even 3, 4, 5, 8 like this. But inverter has only one input. So input is 0, output is 1, complement of A. If input is 1, output is 0, complement of A. So this is called the truth table, the representation of the different combinations of output for different combinations of input is called truth table. Rather, I should say combination of outputs. The outputs for different combination of inputs is give the truth table. The symbol is like this, an arrow type of thing with a bubble, which represents the complementation. If you're using ICs, that day maybe you have seen some IC. The IC number is 7404. Somebody was asking what is 74. This stands for the TTL series. TTL means transistor logic. Okay, this use bipolar transistors, not MOS. If you use a 74 TTL series. Okay, next, these are the NOT. There are 3 basic gates or fundamental gates. One is NOT, another is AND, and third one is OR gate. Okay, other gates are different. Now, what is AND gate? AND gate is called the logical multiplier, and the IC number is 7408. Don't have to remember the IC number. Just for completeness, it is given. Here, AND is the logical multiplication. That means when you see, this is the symbol of an AND gate. symbol of an AND gate. So this is a 2-input AND gate. You cannot have a single input AND gate. You can have 2 input, 3 input, 4 inputs, all possible. But just for simplicity, we are showing 2-input AND gate. So there are 2 inputs, A and B, and the output as usual is Y. Sometimes it is represented as F for Finland, F. So Y or F, in this case Y, it is A dot. Dot means AND. So it is not read. Suppose you have a decimal number, it is 57.63. It is called 57.63. Okay. So 57.63 is a decimal representation, but you don't read this as A dot B. You read this as A and B. Okay. So output is A and B. That's why it is called AND gate. So it is used to perform logical addition. Now this is the truth table. Again, truth table. There are 2 inputs means how many possibilities? 2 to the power of n. Okay. If there are 3 inputs, how many possibilities?
Sir, 8.
8. If there are 4 inputs, how many possibilities?
16.
Very good. If there are 2 inputs, 2 to the power of 2, that means 4 possibilities. What are these 4 possibilities? 0, 0. Both inputs can be 0. For A input can be 0, B input can be 1, or the reverse. That means A input can be 1 and B input can be 0, or both inputs can be 1. So these are the input combinations. Now what is the output? It is A and B. The logical expression for this is that output. Now before I say that, I will say one more thing. This 0 is sometimes said 0, this is sometimes said 1, or it can be said as low. 0 can be said as low, or this 1 can be said as high, or this 0 can be said as false and 1 can be said as true. Okay, so there is various ways you can say this. So output is true, or output is high, or output is 1 when both inputs are 1. Output is high when both inputs are 1. That is the AND gate. It is basically multiplication. It is called a logical multiplication. So 0 into 0 is obviously 0. 0 into 1 is 0. 1 into 0 is 0. 1 into 1 is 1. But we don't say multiplication like that. We don't say 0 into 0, but we say 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1. So this is a AND gate. Is it clear?
Yes, sir.
Yes,
The
sir.
third and the last logical gate is the OR gate. This does logical addition. Okay. The symbol is like this. You can have 3 input, 4 input OR gates. Now here is shown is 2 input OR gates. Since there are 2 inputs, there can be 4 possibilities: 0, 0, 0, 1, 1, 0, or 1, 1. Now Y is the output is equal to A or B. It does addition, but we don't say plus B. It is written, it is read as A or B in digital logic. But actually it does sort of addition. So 0 plus 0 is 0. Actually it is 0 or 0 is 0. You can read it as addition. So 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is how much? Don't see this. 1 plus 1 is how much?
1.
2. Okay. I'm saying in decimal we say 1 plus 1 is 2, but actually this is 1. You cannot have anything like 2. So output is high or output is true when any or both inputs are true. Any or both. Any means either B or A or both. If either B is high or true, or A is high or true, or both are high or true, then output is high. And if both are 0, that means both are low, logic low. It is called logic low. Then output is also logic low. Okay, this is the third fundamental gate or basic gates. Now we come to 2 other gates which are not basic gates. These are called universal gates. Universal gates because you can make other gates using this gate. Okay. Any electronic function you can use you can make using any of these fundamental gates. That means using NAND, you can construct any gate. So what is NAND? You see an AND word here and then an N. So N and NAND, it is called NAND gate, is basically AND plus NOT. So you see an AND gate here on the left. So AND gate, if you put a bubble, that means you do a complement, you will get a NAND gate. So AND plus NOT, this is an AND logic represented by this symbol, and there is a bubble. Here you see there is no bubble. There is a difference between AND gate and NAND gate. Why there is a bubble at the end? Bubble represents a NOT representation or complementation or complementary or negation thing. So here again you have a truth table. This in the truth table, this column is never there. Actually, it is shown only for explanation, but this column is not there in a truth table. If you are told to draw a truth table, don't write this. It is an AND representation, but for explanation it is mentioned. So we know this table up to this third A, B, and AB column we know for the AND. AND is logical
Yes.
multiplication. So 0, 0 is 0, 0, 1 is 0, 1, 0 is 0, logical multiplication, and 1, 1 means 1. Now, after this AND function, we add a NOT function. So this output is just an inverse of or the complement of this. So 0 becomes 1, 1, 0 becomes 1, this 0 becomes 1, and 1 becomes 0. Clear? And this representation is A, and here it is A and B. You see for AND gate, for NAND gate, it is A and B with a bar here. Bar means complement. Is this clear?
Yes, sir.
Yes.
So the IC chip number is 7400 for NAND gate. It's the 74 series starts with NAND gate 00. NOR gate is what you could expect NOR gate to be OR plus NOT. The IC number is 7400. What does an NOR gate look like? It should be OR plus NOT. What is OR? This is an OR gate symbol. So NOR gate would be, there is a bubble here, would be a NOR gate. Clear or not?
Yes, sir.
And the output Y will be A plus A or B, and then a complement bar on the top. So whatever output you get for OR gate, the complement or opposite of this becomes the NOR gate output. So output would now you'd expect is 1 0 0 0. Let's see. So this is the NOR gate representation I told you. OR gate followed with a bubble. So output is A or B and with a complement. This is the truth table for NOR gate, but don't include this. This is only for explanation. This is OR, and then you get a complement of OR. So OR is a logical addition. So 0 plus 0 is 0. Actually 0 or 0. 0 or 0 is 0. 0 plus 1 or 0 or 1 is 1. 1 plus 0 or 1 or 0 is 1. 1 plus 1 or 1 or 1 is 1. So just a complement of this becomes 1 0 0 0. Clear? There is another
Yes.
type of gate which is called exclusive OR gate. These are last two. After this, there will be no such gates. So there will be last two. This is the exclusive OR gate. So it is just like OR, but I'll tell you what this is. Here is a symbol, just like OR, but with a gap and then a bar. This is a curved line, and the input lines end here. Okay. So output is like this. It is called a non-equivalent gate. XOR gate, which has IC number 7486, is called a non-equivalent gate. Non-equivalent gate, remember this, it will be clear, when both inputs are non-equivalent. That means A is 0, 1, B is 1, or A is 1, B is 0. That they are non-equivalent. When it is non-equivalent, output is true or high. When they are equivalent, 0 and 0, output is 0. 1 and 1, output is 0. That means when both inputs are same, output is 0. Clear? So XOR is a gate in which unequal inputs create a high logic level output, and if both inputs are equal, the output will be low. Clear or not?
Yes, sir.
So both inputs same, 0 0 or 1 1, output is low. If inputs are different, output is high. How is the representation? Why it's mentioned as a combination of two inputs, A and A as well as B? I'll use word as well as A as well as B. What is the symbol in between? A circle with a plus sign in between. A circle with a plus sign in between is called an exclusive OR. And if you expand it, it becomes A bar B plus AB bar. What is this bar and all these things? I have told you bar is a complement, but this is a logical expression of two parameters. I'll explain this in details. Now we come to the exclusive or NOR gate. Exclusive NOR gate is like this. It is called an equivalent gate. That means when both inputs are same, either 0 0 or 1 1, then the output is high or true. That's why it is called a equivalent gate. Okay, one, when both inputs are equal, you get an equivalent gate. So it's basically a gate in which equal inputs create a high logic output, and if both inputs are unequal, the output will be low. Unequal means A is 0, B is 1, or A is 1, B is 0. Then the output is 0. Otherwise, it is 1. Symbol is just exclusive OR gate followed by a bubble. Clear? Because if you see this is 0 and corresponding to this is 1, this is 1, this is 0, this is 1, this is 0, this is 0, this is 1. It is just a complement of the exclusive OR gate. It is the NOR gate. So there is a bubble at the end. How do you represent it? A and then a circle with a dot in between, not as plus. Plus means exclusive OR. Circle with a dot is exclusive NOR. And the representation method, expression, logical expression is AB plus A bar B bar. Is it clear?
Yes, sir.
Just a minute. Now I told you these three gates, not and or. These are the three basic fundamental gates. And then you have two gates, NAND gate and NOR gate. Using either NAND gate or NOR gate, you can construct any circuits. So that's why these are called exclusive gates. The first three inverter or NOT gate, AND gate, and OR gate are called the basic gates or fundamental gates. Then you have NAND gate, NOR gate, which are universal gates. And then you have this exclusive OR and the exclusive NOT. So you have basically 7 types of gates which you have studied. Okay. Now I'll tell you one more thing. Now I have told you that this NAND gate and NOR gate are called what?
Universal gate.
Universal gate, yeah. So basically you can construct any circuit using NAND gate. So favorite question sometimes in the examination is to construct the fundamental gates using the fundamental gates are the basic gates. That means and or are not using the NAND gate or the OR gate. So this is basically, I'll come to this later. I will just tell you one example. This is one 2-input NAND gate, and there is another NAND gate. So this is 2-input NAND gate is A bar, B bar, and this is followed by, so this is an inverter function. So in the inverter function, you get the AND gate. Okay. So basically you can construct AND gate, OR gate, NOT gate, exclusive OR gate, exclusive NOR gate, all these combinations using only NAND gate. So I'll come to this later, just as a glimpse of this. Similarly, using only NOR gate, you can make any gate. Is it clear?
Yes, sir.
Now there are uh, some Boolean algebra in expressions which you must know. I'll just give you a glimpse because there are only 10 minutes left. So I told you AND operation is basically a logical addition. Sorry, multiplication, is it not? So we write zero. There are four combinations. The truth table is truth table representation of AND gate, which you have seen here. Truth table representation of AND gate is just written in the other way. That means the expression wise. So it is written 0.0. That means 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1. So that is represented and shown here. That is the axioms, written as axioms. So these are the axioms or laws of Boolean algebra. Similarly, OR operation means, I told you OR is basically logical addition. So you can write A, you have to write A plus B while writing, but reading you have to say A or B. So 0 plus 0, that means 0 or 0 is 0. 0 or 1 is 1. 1 or 0 is 1. 1 or 1 is 1. Okay, is it clear? So these expressions which you found in the truth table are written in a expression form. 0 or 0 is 0, 0 or 1 is 1. 1 plus 0 is 0, 1 plus 1 is 1. Not operation is very easy. 1 complement is 0, 0 complement is 1. Now these are the laws. Based on the axioms, there are some laws. So 0 complement is 1, obviously. 1 complement is 0, obviously. Now if A is 0, then A complement is 1, obviously. From the truth table you can understand. Yes or no?
Yes, sir.
If A is 1, then A complement is 0. Yes or no?
Yes, sir.
Now if you make a complement twice, what do you get? You get back the original. দুবার উল্টালে কি হয়? একই জিনিস, অরিজিনাল জিনিসটা ফিরে আসে। Yes or no?
Yes,
Yes,
sir.
sir.
So you make two complements. That means 2 bar means twice complement. You get back the original. Okay, AND law. I'll just go through this. I'll send you across this handout. AND law is basically AND is a logical multiplication. So A and 0 is obviously 0. Multiply anything by 0, you get 0. Yes or no?
Yes, sir.
This is called null law. A and 1. Multiply anything by 1, you get back what you got actually. 7 into 1 is 7. 24 into 1 is 24. Like this, anything, any number A. This is called a literal or operand. So this is A and 1 is A. 7 into 7 is not 7. 7 into 7 is 49. But here this in Boolean algebra, A and A is A. Remember, 1 and 1 is 1. In logical, it is called logical multiplication, and is logical multiplication, not normal multiplication. In normal multiplication, 7 into 7 you got 49, but in logical multiplication, 7 into 7 is 7. Clear?
Yes, sir.
Why is this A and A bar 0? A is any variable now. A can be 0 or 1. If A is 0, then this is 0, this is 1. What is 0 and 0 is 0. If A is 1, then this is 0. So 1 and 0 is what? 0. Yes or no?
Yes, sir.
Yes.
That's called AND laws. OR laws is logical addition. A plus 0, that means A or 0 actually. A or 0 is A. It is called null law. A or 1 is 1. A or 1. Whatever you add to 1, you actually get 1. So if you add 0 with 1, you get 1. If you get 1, you add 1 with 1, you get 1. So whatever you add with 1, you get 1. Another thing is like you have A and A is A. Similarly, A and A is 1. A and A is 0. Sorry, A and A is equal to A. That means 0 plus 0 or 0 is 0. 0 or 0 is 0. 1 or 1 is 1. So same thing, you get back the same number. If you add 0 to 0, you get 0. You add 1 to 1, you get 1. Here, this is very useful for manipulation. You have A or A complement. A plus A complement is actually 1. Okay. Because if A is 0, this is 1. If A is 1, this is 0. So it becomes 1. Commutative laws, you are aware, if you just interchange the order, it remains same. A or B is equal to B or A. A or A and B is equal to B and A. Associative law, associates. Whether we associate with A, whether you associate B with A like this or you associate B with C, it remains same. Similarly, if you associate B with A or you associate B with C, it remains same. Distributive law, just like in algebra, it is true here. A bracket में B plus C, it becomes AB plus AC. Here A plus BC you get from the first one. This is the just invert the end of the order. This is called the duality principle. I'll come to the rest later on. Okay. We have run out of time. Next class is on 9:30 Wednesday.
Yes, sir.
Shayon,
Present, sir.
Shivam, Vishwadip,
Yes, sir.
Prince,
Present, sir.
Shojash, Anu, Tushar, Rajat,
Present, sir.
Devanta,
Present, sir.
Ayush, Almukund,
Present, sir.
Saket,
Present, sir.
Aditya,
Present, sir.
Aditya,
Present, sir.
Anub,
Yes, sir.
Abhishek,
Present, sir.
Priyanshu,
Present, sir.
Arinda,
Present, sir.
Alokeshwar,
Present, sir.
Anurna,
Present, sir.
Aman,
Present, sir.
Harshneet, Priyanka,
Present, sir.
Devdatta,
Yes, sir.
Mohammed Hamidul,
Yes, sir. Present.
Sagarika, Abhishek, Sheikh Nishan,
Present, sir.
Anisha, Nishant, Akrur, Abhishekta,
Yes, sir.
Rajeshwar, Arnamoy,
Present, sir.
Joy,
Present, sir.
Mohim,
Present, sir.
Moshana, Ramesh,